property, use of it, especially in chemistry, accounts. Okay. Our speaker today is Sarah Bittner. She drove up a long way from Houston this morning. The weather was much nicer down there than it is up here. So be grateful to her for coming up here in the frozen north. Yes, doing that. Sarah got her bachelor's degree in chemistry from the University of California in Berkeley. And she got a PhD in chemistry from the University of Chicago in theoretical chemistry. And since then, she's not only worked in chemistry, but she's also worked at a number of law firms as a patent agent. And she's going to tell you a little bit about her life experience and careers in patent law, and a little bit about the direction of patent law with respect to what's all like. So let's give Sarah a warm welcome.
Well, thank you. It's a real pleasure to be here. And since I understand the audience is a little bit mixed, I kind of want to get an idea of who all you are first. So if you're studying any kind of engineering, can you raise your hand? Okay, of those, who's studying chemical engineering? One, two, three, okay, a few over there. Okay, so how many are studying straight chemistry, not engineering? Okay, a few. And how many of you are studying computer science? Okay. So interestingly enough, even though the topic is ostensibly about chemistry, the chemists are in the minority in this room. All right, so one disclaimer, I work at Chamberlain Hurlica, which is a law firm, but I am not a lawyer, and nothing that I say to you is legal advice. Sorry, the arrows aren't working. Unless I need the, nope.
Sometimes you have to click off someplace. And then it starts working. There you go. So now it should work. Oh, I gotta go down.
All right, fine. Yeah. Gotta go down. Gotta get my directions right. All right, so what is a patent? It's a type of intellectual property. So intellectual property is property that protects basically your creative output. And it gives you a right to exclude others from making, using, selling, or importing the invention as defined by the scope of the claims in the patent. And it has a limited duration, and currently that's 20 years from when you file your application. And it doesn't actually give you the right to practice your own invention, because somebody else might have a patent that covers part of what you want to do, and you would have to deal with, say, getting a license from them first before you could actually practice your invention. It just gives you the right to stop other people from doing what you patented. Okay, so this is an example of a very famous patent claim. And interestingly enough, today, if you go to Target or Walmart and you buy a little Play-Doh, and they've got these little tiny ones that we use for demonstrations, sometimes the party favor size, and we'll pass them out when we're talking about like what are patents and what's intellectual property. And if you look at a Play-Doh container, it will have markings for patent numbers, some newer patents, this one's expired, some trademark indications, and some copyright indications. So you can see 3 different kinds of intellectual property all there on the Play-Doh container. So this is an early Play-Doh patent, and it was issued January 26, 1965, and it was in a previous era when you determined the duration from when it issued, and it lasted 17 years from issuance. So it's long since expired, which means that anybody in the public can do what's described in this claim. A claim is a statement that describes in words the scope of your invention. So note that we're describing something technical, but the means with which we need to describe it is the English language. So that's one of the challenges for the computer science people in this room. If we want to try and do quantitative approaches to thinking about patents and our other patents nearby, I mean, how do you define that when you're fundamentally dealing with words? So this has, the first part is what we call the preamble, and it starts saying a smooth, velvety composition of matter, which soft, pliable, non-sticky, and non-toxic. And Play-Doh is still primarily the main product that you can buy that has these characteristics. What else? Lump-free, reworkable, remoldable. And they're saying consistently, essentially. So that's a sort of a specific kind of a legal phrase, consisting essentially, which means that it doesn't have anything else in it that detracts from its properties. So it mainly has these ingredients. It could have other stuff in it, but as long as they don't mess with all of these characteristics. So the other thing, notice that there's quantities. There's this word about that chemists appears in all these chemistry applications, and about is one of those words that people fight over. What does it mean? Nowadays, people typically define it. It could mean plus or minus 10%. It could mean plus or minus significant figures, plus or minus standard deviation, some technically reasonable sort of wiggle room about the numbers that are given. Because what you're trying to do is make sure that if, like, say your competitor does it at 449, you still want to be able to prevent him from what he's doing. So if he's like really close to what you're doing, you still want to be able to stop him. So that's why people use words like about. Then notice that this is the quantity. This is just a raw quantity. You don't see that much these days. Usually it's like the fraction of the composition is this component. So we've got grain flour, we've got water, and this surprised me, we have kerosene, and then there's an inorganic chlorine salt. So table salt is a chlorine salt. It's sodium chloride. And inorganic, of course, means that it's like, say, sodium or other elements that are not carbon-based. So that is what a chemical composition statement that defines an invention can look like. And like I said, those statements are generally called claims. So there's another type of chemical claim that you can see, and this is another very well-known patent, and I'll explain why it's well-known later. But this is from Idenix, and this one was filed May 23rd, 2000, under the regime where the duration goes from the effective filing date. So it lasted 20 years, so it's due to expire if there aren't any term adjustments, which there can be, but we're not going to get into that. It's due to expire, this spring. So this is now a process, and it's a method of treatment, and a lot of chemical applications are methods of treatments, because one of the big areas of chemistry, if you're not making, say, plastics, is making drugs. And so this is a patent about a drug. It's a hepatitis C virus treatment. So the method comprises administering an effective amount. You see that in pharmaceutical applications all the time, talking about an effective amount. So we have a purine or a pyrimidine, and if you've had organic chemistry, I believe those are ring structures. And so this one is a complicated, generally these pharmaceuticals are somewhat complicated, unpronounceable compounds. And so it's this compound or a pharmaceutically acceptable salt or ester thereof. And if you've had organic chemistry, an ester is a derivative and a salt is just, the thing, it can complex with an ion and form a salt. And so backing up, that just illustrates two different types of patentable subject matter. So the first one was a product. We had a composition of matter. There are other products that you can patent. You can patent a manufactured item. You can patent a machine. There was a well-known case that happened recently that was about a garage door opener. You can patent garage door openers. You can try to patent the electronic control of the garage door opener, and unfortunately these people, that was ruled unpatentable, and there's a lot of controversy about that because you'd think that something physical like a garage door opener would be patentable, but they said it was an abstract idea because mostly it was concentrating on the controller software. And software, so you can also patent a process, a method. What you can't patent are a law of nature or an abstract idea. And that's where it can be challenging to patent software or diagnostic methods. And it's challenging to craft the patents in such a way that they're considered concrete enough to not be an abstract idea. And it's very controversial. There's people on both sides. There's some people who don't want there to be any software patents. There's other people who want it to be easier to get a software patent. There's some people who don't want you to be able to patent any diagnostic method because it should all be there for the public. There's other people who say none of these companies would develop the diagnostic methods if they couldn't patent them and get a return on the investment. So those are two of the areas where it's kind of challenging. All right, so to enforce patents and to obtain patents, the various government entities play a role. So you enforce patents in the federal courts, and the district courts have jury trials, which can get really interesting. So you're trying to explain this complicated technology to the juries, and then the juries decide whether or not the alleged infringer has infringed the patent. And then the losing side sometimes appeals, so you go to the appellate courts, and then sometimes it goes all the way up to the Supreme Court. And some years there might be a few patent cases, some years there might not be any. The Supreme Court, I think, normally takes 60 to 80 cases a year, so there might be a few, there might be none that are about patents. On the other side, to obtain a patent, you apply for your patent with a federal administrative agency that's called the United States Patent and Trademark Office. And there's different people that are involved in these different actions, enforcing the patents and obtaining the patents. And I'll get to that later, because I'm going to talk a bit about the kind of people that are involved in this universe of patents. But first I'm going to explain what was unique about this Idenix patent about the hepatitis C treatment. It was the biggest patent verdict in U.S. history at the time of the verdict, which was around 2016. It was $2.54 billion. So Not all patent judgments are that large, but they can be very, very large. And Idenix Pharmaceuticals is a Merck subsidiary, and they sued Gilead Science and said that they were infringing their patent for hepatitis C treatment with their sales of Salvaldi and Harvoni. And in all likelihood, after this judgment, the first thing that Gilead would have done would be to file an appeal and protest the judgment. And given that it was 2016, I don't know if if the litigation would have finished yet. And I don't know the status of it. I didn't look it up. Mostly here I was just pointing out how large the verdicts can be. And so that's one source of the big ones, actually, is with chemical patents. All right, so now I was going to talk about scope. So scope is a concept that's very central to the world of patents, but it's one of the concepts that can be somewhat challenging for people to pick up. And to enforce a patent, the infringing product or process must be within the scope of the claims. So the claims will have some scope, and you need to be able to show that this alleged infringing product or process falls within that scope. So it falls within the scope of what you have the right to exclude people from doing. To obtain a patent, on the other hand, the claims need to be outside the scope of what's called the prior art, which is things like patents, publications, public disclosures, generally things that were already known before you apply for your patent. And two elements of this is that your patented subject matter that you're applying for needs to be new, and it needs to be non-obvious. And if it's not new, that means it's wholly described in, or one of the ways it can be not new is that it's wholly described in some earlier public disclosure, either in a patent or in a paper. So that means that, say you're publishing a paper, you've done this really cool result, and you're going to go publish it. Depending on your university and depending on whether, what your status is in the university, if you're an employee or a student, and it varies from university to university, you might be suggested or required to tell an office within the university that you've come up with some cool new thing and give them a chance to try and patent it before you publish it. Because once you've published it, actually, the U.S. has a grace period of a year, but other countries don't. So if you want any kind of international patent coverage, you have to file your application before you publish it. And non-obvious, people that you can, non-obvious has to do with, based on the totality of what was known at the time, would it have been obvious? And when the patent office is saying that you can't get a patent because it's obvious, they can combine multiple references. So they might combine 2 or 3 different patents and say, this one teaches this piece, this one teaches this piece, this one teaches this piece, and it would be obvious to put them together. And obviousness is very complicated, and it can get very fact specific. So anyway, I'm talking about scope. So a lot of times people think of scope somewhat spatially as an analogy. So if A is the entity or the company that has the patent, they want the product that they're alleging is infringing to be within the scope. And they want what was known before to be completely distinguishable from the scope. So in this diagram, I have shown it with these ovals and circles on the paper. The paper is sort of living in Cartesian coordinates, and so there are distances on the paper. But that is, if you're measuring distance, you can take out your ruler and you can quantify the distance, and as long as you're not measuring the distance on a fractal structure, the distance is very well defined. And for people who are up on math, what the lingo is that it's a metric space. So you can define what distance means, is essentially what that says. And this ability to quantify distance has not really been realized for patents. And part of the challenge, again, is that you're describing technology with words. The Patent Office has a classification system that some people use to develop routines to define distance. And one of the interesting things is that the effort to define, if you could define distance and quantify them, you might be able to develop an artificial intelligence system to predict things like, say, what are the chances I'm going to win if I sue this guy? Or what are the chances that I'm going to get this patent claim given what's already known? And so you could, in principle, begin to make these quantitative predictions using software. But right now, it's an art. Figuring out the nearness and farness in the patent world is definitely an art. It's not a science at the moment. And it's qualitative and it's not quantitative. One of the interesting things, I think, is that this is an area where people are actually trying to get patents. So there are patent applications about how to quantify the world of patent applications and patents. So that's the way A would like to look at it. B, the accused infringer, wants this to be the layout. So they want the claim to fall entirely within the prior art, which means that it would be invalidated. And they want their product or process to be entirely outside the scope of the claim so that they would be determined to be non-infringing. And so if one party brings a lawsuit against another, they will both have opposite positions on validity and infringement. All right, so there's a quid pro quo that goes with getting a patent. So you get something when you get a patent, you get the right to exclude. What you're supposed to give is that you're supposed to describe how to make and use the invention in enough detail so that anybody could reproduce it. So one of the risks in a way these days, so unless you only file in the United States and request non-publication, your application will be published within 18 months from your filing date. So part of the process also of figuring out if you're going to file a patent is, well, are you going to be describing it anyway? I mean, in the university context, it's often an easy question because you're planning to publish it anyway. So you might as well file for a patent application. But say you're in a company and you don't know whether to make it public or not, well, you want to have a good chance of actually getting a patent, because otherwise, if you don't get a patent, you've explained it to everybody, but you don't have a right to exclude anybody from doing it. So you've basically just given it away. So again, this is sort of a reframing of an earlier slide. What you get is you receive granted claims, and they delimit the extent of your right to exclude others. And as I said before, it's not a right to practice the invention. That might depend on other people's patents. So, as I said, a patent is a document. You can look them up on Google Patents. If you go to Google and you Google Patents, Google will give you the site of Google Patents, and you can search Google Patents for all kinds of technology. It can just accept, you can just type in a word, like say you want to know patents on chairs. If there's any patented chairs, you could search for chairs. And then Google will let you specify things more finely if you want to. It pulls up an interface on the left, and you can put in like inventor names, you can put in company names, but that's a publicly available source of actually international patents. And patents are geographical, so if you get a US patent, you can only exclude people in the US. If you get a French patent, you can exclude people in France. If you get a German patent, you can exclude people in Germany. There are international applications that are kind of placekeepers, but then after a certain period of time, you have to go into what's called the national phase and file in the various different countries. So the pieces of the patent document, at the beginning, there will be an abstract. Then there's what's called a specification, which has text and drawings. If drawings are essential for describing the invention, which they often are for mechanical inventions, then there need to be drawings. And also, flow diagrams are often required for software inventions. And then at the end, you'll have the statements that are the claims. And, all right, so this is a statement that people like to quote. It's an old Supreme Court case from 1892 where the judges said that the specification and claims of a patent, particularly if the invention be at all complicated, constitute one of the most difficult legal instruments to draw with accuracy. Nevertheless, people with technical training who haven't gone to law school, like myself, can end up working in law firms, writing patent applications and helping people get patents, because part of it is, it's partially about this phrase, particularly if they be at all complicated. You need to be able to understand the technology to do a good job of describing it. So the people that are involved. To enforce patents, you have lawyers. And for example, this is what the Idenix team did, and it's fairly common. You combined attorneys who specialize in litigation, but aren't registered to practice before the patent office. You can get, the states have their bars, so you can be a lawyer before the Texas State Bar and allowed to practice law in Texas. And then also, to help someone get a patent from the USPTO, you need to pass a different bar exam, which is the patent bar exam, and then you're registered to represent people before the USPTO. And you can sit for the patent bar exam without being an attorney. And then a patent attorney has passed both of them. So they'll often pair intellectual property attorneys with general litigation attorneys, and they play different roles in the litigation. Then to obtain patents, you need to be a registered patent practitioner, and that includes patent attorneys who are lawyers and patent agents who are not lawyers. Now, patent agents and accountants are the only two types of professionals that are allowed to represent people before the federal government who are not lawyers, but they're specialists in their particular area. And in order to be able to even sit for the exam to become a patent agent, you need a science or engineering degree, or effectively the equivalent. Like there's a way in, if you don't have a standard science or engineering degree, to show that you've had an equivalent amount of science and engineering classes, but it's easier to just have a straight up degree. And with computer science, they're a little bit strict with computer science degrees, and it needs to be accredited. And if it's not accredited, then you need to go in through that alternative route of like just totaling up your science and engineering classes. So there's different accrediting agencies. They accept ABET accreditation, and I think there's a couple of other accrediting agencies. But I know a computer science degree can either be accredited or not. I know UT Austin's is not accredited. UT Dallas's is accredited. A&M's is. University of Houston is. It varies from school to school, whether it's accredited or not. Okay, so then I wanted to talk a little bit about some specific people, and I've ordered these people from junior to senior. This is our team at Chamberlain, and I've ordered them from junior to senior, which mostly it tracks when they got their law degree. And you will notice that there are some of the older people are actually some of the junior people in the ranking. So, but the ultimate ranking in the law firm is when did you get your law degree? And then, by and large, that's a simplification. But our newest edition that's on our website is Brady Burns, and he's a technical advisor. And he graduated from Trinity with a Bachelor of Science in Engineering Science in 2019. So he's been working for us for about 6 months. And the way he came to the firm is that there's a more senior member of the team who graduated from Trinity who, when we're looking for somebody, he calls up one of his old professors and says, "Do you have any recommendations for us to interview?" And so far, there have been 2 people who've come to us that way. So there's Brady, and then there's Ivan, who also has a BS in engineering science, which is a general engineering degree. That's the only engineering degree that Trinity offers, is my understanding. And he's also what's called a technical advisor. So a technical advisor is somebody who's in training, essentially. Ideally, they sit for the patent bar exam and they become a patent agent, and then they can work more independently. And both Brady and Ivan are from the Houston suburbs. They're local to Houston, and they went to Trinity for college, and then they came back to Houston to live. And so what I want to point out is that this is a career path, if people are interested, that you can jump into straight out of college. And Chamberlain is not the only law firm that will train people. Osha Liang is another one in Houston that does this, and there are a number of others. And Fernando Puna, his background is electrical engineering, and he was in the technical area for a while. He was actually in a PhD program, and his advisor left, and it created a bit of a difficulty for finishing the PhD program, and he decided to just exit with a master's. And now he works for Chamberlain and works very hard and is very good and is part of the team that works on computer technology, software, those kinds of inventions. And then there's myself, and as was noted, I got a bachelor's degree at Berkeley in '85 and a PhD in 1990. And I was in the midst of what's called, sort of jokingly in the physics community, the two-body problem. Now, if anybody's familiar, the three-body problem is generally known to be unsolvable. So the two-body problem in physics is solvable, but the joke is that the two-body problem analogy can be unsolvable, and that's where you. And again, at the time, this was a while back, and things have changed a lot. But when you had two people who were married to each other that were in similar fields, it can be really difficult to get jobs in science in the same place, especially if you were both looking for academic jobs. And so I ended up flexing, and I completely shifted, and I started working at a law firm. And in those days, there was a lot of activity that involved high-tech aspects of chemistry, and there weren't enough attorneys who had the background, and so they were training people, and I didn't know anything about patents when I started the job, and I got trained on the job. And it's actually pretty fun because you get to learn new technology again and again and again. So if you like learning things, if you like challenge, it's a fun thing to do, because rather than going into depth about one thing, which is a great thing to do, but you get to be sort of, our inventors might have worked on their invention for 5 years, and then we get it, and we need to write up the patent application in 30 hours. So the challenge is to be able to quickly understand what they've done and then figure out how to describe it in words accurately and in such a way that they're happy with the way you described it, all within a fixed amount of time. And Tony, I recently passed the bar. He was working as a tech advisor for a while, and he is going to be taking the patent bar soon. And he's has a lot of experience. In terms of experience, he's one of the more senior people. And he works in, you're going to notice a lot of these bios, the field is electrical engineering. That's because we've got a lot of that kind of work in the firm. And Justin was mechanical engineering. He also works on the team that does a lot of patents on computer inventions. And he also recently got a law degree. And he went a bit more quickly from engineering to law. I mean, he basically graduated, looked around, and decided, I'm going to go to law school. And then Jeff, he's our Trinity connection. And he is another one that has a degree in electrical engineering. And he's fairly experienced, has been training some of the newer guys. So like Tony and Jeff are training Ivan and Brady. And then we have Matt, who works on the team. We have two main teams under the two main attorneys, and except for myself, all the other people I'm describing to you work on Allie's team, and that Matt and I both work on Colin's team for Colin's clients. And he has a mechanical engineering degree from Texas Tech, and his law degree is from University of Houston. And that's a theme you'll notice. All the attorneys that we have got their degree from University of Houston. Ali is one of the shareholders. He got his degree in Canada. It was a mixed degree in chemistry and computer science, but now he's mostly using the computer science aspect of it, and he has some big clients that give the firm a lot of work in the field of computers and software. And then Colin is the most senior person. He graduated from law school in 1999. And he has a number of oil and gas clients, and that's the sort of work that I've been doing. And before I was at Chamberlain, I was actually working what's called in-house in a company as a patent liaison, and it was an oil and gas services company. That its big thing actually was computations, because if you're trying to solve for the structure of the Earth, it's an inverse problem, and you're dealing with terabytes of data, and even with today's computers, you cannot brute force invert those matrices. And so it's an art. You need to figure out what approximations to make, and they make some approximations, run the code, and the room with the computers, it was enormous, and a lot of the code was running on graphical processors that were oil-cooled. And it was kind of a fun, exciting computer room. And I originally worked, when I started, I worked at a firm called Conley Rose, and the Rose was David Rose, who's Colin Rose's father, and I had known Colin then because he actually came to work with the firm for a while, and I went off and was working someplace else, and then we reconnected again recently, and it's been rather fun. So I'm going to jump through this because we're running out of time. This is just pointing out that there's patents in other countries. Universities can own patents. They can have some pretty big deals. Stanford got a bunch of money from the original Google patent. And Northwestern developed Lyrica and got a bunch of money from Pfizer and has invested it. I thought this was kind of impressive. Now the money from that makes up 18% of their endowment. And a plug for one of your classes here. To learn more about patents, you can take Political Science 3223, if I'm getting that number right, Patent Law for Scientists and Engineers. And that's the end if you would like to ask some questions. Yep.
It seems like a lot of patents go for, or it makes more sense to do a patent if you have some like huge amount of money involved with it, or like it's going to be, I don't know, revolutionary and everyone's going to want to steal it from you. But if you're doing something, I don't know, really small, like some small invention for a university, can it still be worth it to like do the whole investment for that kind of thing?
Yeah, it can be worth it. And in terms of the economics, the verdicts can be really huge, but those are rare. And overall, the price to get a patent isn't so much. So generally speaking, to go from the beginning until the patent issues, it's $20,000 to $30,000. And so it's a fair amount of money, but it's money that universities are often willing to spend. And I have worked with another law firm that had a number of university clients, and some of those universities had undergraduate engineering classes where they would give the class a project to do, and out of that project emerged an invention. Like, for example, one of them was a project that had to do with a portable cooler for insulin that used the thermoelectric effect, and it was all sort of motivated because the guy who's teaching it, his wife was diabetic, and they liked to travel overseas, and refrigeration was hard to find, so they wanted to be able to like charge it up, say overnight, and then have the cooler last and keep it cool until they reached electricity again. And I worked on writing that patent application, and there were a whole bunch of students who were inventors. But in that particular one, the university ended up releasing the technology to the professor, and then when there was an office action and the patent office said, oh, it's not patentable, he decided at that point not to continue. And the clients of law firms sometimes do that. I mean, they make a decision and they say, well, yeah, I could maybe get around that piece of prior art, but it's going to narrow the claims so much that I don't really value it enough anymore, and they just stop. But and I know various different schools have different policies. I haven't checked, so I really don't know what your school does, but one of the ones I looked at for my son, Worcester Polytechnic, they have a patent, they have these project classes, and they have a patent policy that all of the students sign that the school will own the rights to the inventions that they invent while they're in the class. And there are certain advantages to that in terms of licensing, because licensees want the process of getting the rights to the patent to be fairly easy and straightforward. And when you're just negotiating with the university, it's easier than when you're, say, negotiating with 6 students that all own the rights. Sometimes students form a company. Sometimes they have a parent who helps them form a company. So there's all different modes, but I would say the bottom line answer is it can be worthwhile to go for a patent. And it's more sort of like, I guess sometimes people know they've got a blockbuster when they invent it. But other times they really don't know, and it plays out, and it might be 5 or 6 years before you know which are the really hot inventions and which are not. So there's more a tendency to look at, like, what is the potential market? Is this kind of cool from an innovation point of view? And then there's analyses that are made and judgments about whether to go forward or not. But sometimes it's just a volume thing. Like in the early days, I think Stanford would patent just about anything that came through their door. And there was another question behind you. Okay. Yeah?
You were talking earlier about trying to patent software. Is that, are most software considered not to be products in that case then?
Well, software, well, the applications are generally written so you're trying to patent a method, and then you're also trying to patent a product. So you get 3 what are called independent claims for the base price of applying for a patent. And so they'll do a method, then they'll do a computer readable medium that's encoded with instructions for the method, and then they'll do a device that includes a processor or a computer readable medium that carries out the method. And so they try to attack it from all 3 angles. Yep.
So how did you decide you wanted to do working in patent law versus just staying in like medical degree?
Happenstance. And that's the key. Actually, a lot of people who are in patent law fall into it. Like, I don't know if you noticed, out of all those bios I gave you, only 2 of them went straight from undergrad to law school. And it makes the profession a little bit quirky. The people can be quirky. But I fell into it. I first found out about it during the coffee hour after church at my little Episcopal church in Austin where I was going, St. Mark's. And I was a postdocing at UT Austin, and I was struggling with, well, what am I gonna do? I've been on the academic job market for a while. It's kind of challenging. The wall just came down. We're flooded with Russians who will work for nothing. It was very competitive. And I was willing to sort of consider all different avenues, companies. And I was talking to somebody, and he said, well, why don't you think about working in the patent field? And he was a patent attorney for Huntsman at the time. I believe it was the one that I met who was at Huntsman. And I remember him saying that to be careful to learn the patent world, that I would need to make the transition into the patent world so that my knowledge didn't just get sort of like used up and spit out by the firm and they would move on to the next person. But so it's like you really have to make a transformation and start thinking more like a legal person, even if you're not a lawyer, and less like a scientist. Like a scientist's instinct is to be really thorough. There's a need in the law firm to be efficient. Your main product is your time. And so if there's a fixed price that's being charged for what you're doing, you need to get it done in a certain amount of time. So anyway, I met that person, and then he told me about this job opportunity. So I called them up and I met with them and I interviewed, but it turned out I called them, like I waited a week, and the problem was that they had already hired somebody, but they said, come in and interview anyway. So I did, and I liked it. It was really interesting. And then I took a job at a startup in San Francisco, and I did that for a year. And then my husband got a job in Houston, and I was the trailing spouse. And I was thinking about what I was going to do. And I was taking a walk in my neighborhood, and I ran into somebody that I tended to run into walking in the neighborhood. And I saw her coming home, unloading her children in a really nice suit at 4 o'clock in the afternoon. And I thought, I want to know what that career is, because I would like to have a professional job where I can come home with my children at 4 o'clock in the afternoon. And I ended up working at her law firm. And about 6 months later, I interviewed, and then they didn't have the right client, and then they ended up getting this big chemical client, and I got a job there. And I never worked full-time for that law firm. And people can complain about billable work and how you have to keep track of your time, and it stresses people out. But one of the beauties of billable time is that it's scalable. So it's easy to say, okay, well, I'm going to work 3/4 of the yearly hours requirement. And as long as the firm can make the economics come out okay and your overhead is covered, they're good. Whereas science research is harder to scale, and it looks like we're out of time.
Is our last question for our speaker here? Is it worth taking a patent law course as an undergraduate?
Well, I think it's worth, more and more people are filing for patents. It's becoming a part of the academic life, so I think it's worth taking.
Okay. Right. Also, before we break up, I wanted to remind you that next week we have David Larry from the University of Texas, Dallas, who's going to talk about smart cities. And we'll see as long as it was a smart city or not so smart. And let's also remember that we have lunch with our speaker today in the Joyce Room of the Corner Cafe. So if you'd like to learn more about life in the law field, after engineering career here at Laterno, come and join us there. Let's also thank our speaker. We'll see you all next week. So we don't have a coffee cup, but we have this autobiography here.
Oh,
of
okay.
Laterno.
Thank you.
Went around the room.
Oh, wow, that's really nice.